Glad to welcome you back to our channel. And today we will continue the topic of new energy storage technologies, which we have already explored in several previous videos. And today we will talk about technologies that are still on the verge of science fiction. That is, technologies based on physical principles already known to us, but whose implementation is still beyond our technological capabilities. Nevertheless, these very capabilities are constantly expanding. So what is currently only theoretically possible may become a reality tomorrow or the day after. And if this really happens, we will be able to obtain batteries based on fundamentally new physical principles, which will surpass the conventional batteries we are familiar with by several orders of magnitude in key parameters. For example, some of the concepts we will discuss today theoretically allow storing tens of thousands of watt-hours of electricity, which already exceeds the specific energy density of hydrocarbon fuel. With such batteries, not only electric vehicles capable of traveling thousands of kilometers on a single charge will become a reality, but also aircraft with electric motors, including flying cars and other cool things like that. So there is definitely a motive to invest effort, money, and time in scientific research in this field, even though some of the things we will discuss today may seem far too fantastic. Well, now let's move on to the battery technologies of the future. And the first type we would like to discuss is superconducting batteries, the so-called superconducting energy storage devices. The idea here is extremely simple. If we create an electric current in a loop of superconducting wire, it will keep circulating in this loop indefinitely without external interference, lasting for years or even decades. Consequently, such a loop itself becomes a kind of electricity storage. If desired, it can be connected to the power grid, and the energy stored in it will be used to excite current in that grid. More precisely, energy in such storages is stored in the form of the magnetic field energy created around the superconductor. Roughly speaking, when we excite current in the conductor, we do work to create a magnetic field. And when we connect our superconducting storage to the grid, the magnetic field prevents the current in the conductor from weakening too quickly. This is similar to how an inductance coil reacts to the appearance and disappearance of voltage in a circuit. We have a separate video on these electrical components and the principles of their operation. In fact, superconducting storage devices are therefore also called superconducting magnetic energy storage systems, and they are usually manufactured in the form of the same coils, but not from ordinary wire, instead using superconducting material. Superconducting magnetic storage devices have several undeniable advantages. First, they have extremely fast response times, meaning we can very quickly switch between charging, storage, and discharging modes. Second, charging and discharging such batteries can happen almost as fast as desired, meaning these batteries give us great flexibility in power output. Third, superconducting coils themselves have an almost unlimited service life. There is essentially nothing in them to break down, which theoretically means the cost of such storage systems may not be too high. Superconducting storage devices hardly lose charge over time, and energy is injected, stored, and transmitted directly as electrical energy, meaning their efficiency is close to 100%. Unfortunately, only a limited amount of energy can be stored in such coils. The problem is that excessively strong magnetic fields and excessively large currents destroy superconductivity. For the best modern superconductors, the critical magnetic induction values are around 20 to 30 Tesla, which limits the maximum specific energy capacity of such storages to no more than a rather unimpressive 50 watt-hours per kilogram of mass, compared to 150 to 200 watt-hours per kilogram, even in conventional lithium-ion batteries. This makes superconducting storage devices practically useless for use in the transportation sector, but due to the advantages mentioned above, they may be useful as long-term electricity storage solutions. Unfortunately, the best modern superconductors, such as yttrium barium copper oxide, require cooling to temperatures around -180 degrees Celsius. This means that superconducting magnetic storage systems also require powerful cryogenic equipment, and such equipment is expensive and also consumes a lot of energy during operation. As a result, the specific cost of superconducting storage is around several dollars per watt-hour of stored electricity, which is an order of magnitude higher than the corresponding figures for lithium-ion batteries, which themselves are considered too expensive for the creation of high-capacity stationary storage systems. In short, widespread use of superconducting storage currently appears irrational and unprofitable. However, if the ongoing global search for superconductors capable of operating at higher temperatures is successful, this technology will have very intriguing prospects, primarily as a balancing element in large power grids, where it could store generated electricity and then release it back into the grid during peak consumption times. Quite often, in the context of electricity storage technologies, various nanostructured materials are mentioned, such as, for example, graphene, which is a sheet of carbon atoms only 1 atom thick, or its derivatives like carbon nanotubes, which are essentially the same graphene sheets rolled into tubes. For example, in the comments under previous videos on battery-related topics, many people asked why I do not mention the so-called graphene supercapacitors. I really have not mentioned these devices, and I do not particularly plan to talk about them now either. And the issue is not even that graphene supercapacitors have a rather moderate specific energy density of about 50 to 70 watt-hours per kilogram of mass. The issue is also not even that the efficiency of supercapacitors, like any capacitors, decreases as their linear dimensions and capacity increase. So high-power supercapacitors will be not only inefficient but also expensive, several United States dollars per watt-hour of stored power. However, the main problem here is that supercapacitors are fundamentally unsuitable for long-term energy storage because they technologically have a high self-discharge rate. Yes, supercapacitors, including graphene supercapacitors, will find applications, for example, for pulse power supply of high-power devices from batteries delivering low electrical power, or for smoothing voltage spikes in networks. But as independent energy storage devices, they are not considered even in the long term, and I see no point in spending time discussing this technology. Nevertheless, there are other ideas on how the remarkable properties of nanomaterials, such as graphene itself, can be used to manufacture next-generation batteries. In our previous video, we already touched on this issue. For example, graphene can be used as a material for flywheels in the so-called flywheel energy storage systems, which in theory may allow us to create storage devices with a specific energy capacity of around 1,000 watt-hours per kilogram of mass. If, of course, we learn how to make something sufficiently large out of graphene, which is still beyond our capabilities. In addition, there are several ideas on how nanomaterials can be used to improve existing batteries. Graphene sheets, being an excellent conductor, can replace metal current collectors. Graphene or carbon nanotubes can be used for mechanical stabilization of the cathode and anode, and so on. There are also other approaches to how nanomaterials can be used for energy storage. A rather interesting option was proposed in 2024 by a group of scientists from the United States and Japan. They put forward the idea of storing energy in the form of elastic deformation energy of single-walled carbon nanotubes. The idea is that many such nanotubes are woven into a kind of nanorope, and then this nanorope is twisted under the action of an external force, storing energy in it like in a kind of torsion spring. Nanotubes, with their negligible density and enormous strength, allow for storing truly large amounts of energy, up to 1,000 watt-hours per kilogram. For example, in the aforementioned Japanese-American study, about 580 watt-hours of mechanical energy was stored in a nanorope made of commercially available nanotubes, which significantly exceeds the performance of lithium-ion batteries. Unfortunately, for this technology to become widespread, we first need to get much better at producing carbon nanotubes with specified characteristics. However, work in this direction is also underway, and not only in connection with new electricity storage technologies. Nanotubes have enormous potential for use in a wide variety of fields, so these amazing structures probably also deserve a separate video on our channel. However, the greatest potential, at least in the long term, is held by a technology known as quantum batteries. More precisely, it is not even a technology, but rather a technological direction in which quantum mechanical effects are planned to be used for energy storage, opening up very intriguing prospects. There are many approaches to creating quantum batteries based on so-called Josephson junctions, quantum dots, micromasers, optical resonance cavities, and so on. It would probably be correct to analyze in detail the principles of operation of each of these proposed mechanisms. But for that, we would first have to explain what Josephson junctions or quantum dots are, and the material would become too extensive and difficult to understand. Therefore, we will take a different approach. In this video, we will consider the most general principles of quantum battery operation without focusing on specific technologies. And then in other videos, where we will analyze particular systems such as quantum dots in more detail, we will touch upon how they can be used to create quantum batteries. Quantum batteries seem quite simple. Almost any quantum systems can indeed have different energy levels and absorb energy from external sources to transition to higher levels, then emit it when transitioning to lower levels. A classical example is an ordinary atom, which can absorb energy to move one of its electrons to an outer energy level. In this state, the atom can be considered a tiny storage of a small portion of energy, which it will release after some time by emitting a photon with exactly the same energy that excited it. In some sense, such an atom can be seen as an elementary quantum battery. Before absorbing the photon, it is discharged. After absorbing it, it is charged, and in the process of returning to its ground state, it discharges. For example, in a single hydrogen atom, up to 13.6 electron volts of energy can be stored in this way. At the same time, in 1 kilogram of hydrogen, there are 6 times 10 to the power of 26 atoms, which gives a specific energy capacity of about 1.3 times 10 to the power of 9 joules per kilogram, or 364,000 watt-hours per kilogram of hydrogen. If we recall that for modern batteries, even 500 watt-hours per kilogram is still considered an unattainable dream, it is easy to see how promising quantum energy storage technologies are. And if we store energy by exciting not the electrons of an atom, but the nucleons of the atomic nucleus, the specific energy capacity becomes truly off the scale. For example, in 1 kilogram of hafnium, 178 in the metastable excited state M2, there is 1.3 times 10 to the power of 12 joules, or 3.7 times 10 to the power of 8 watt-hours of energy. However, using isomeric transitions for energy storage comes with a number of additional challenges, which we discussed in one of our previous videos dedicated to the topic of nuclear isomers in general, and hafnium-178 in particular. All this is wonderful and remarkable, but there is one problem. We cannot control the time an atom or atomic nucleus remains in an excited state, meaning our atomic battery would discharge at a random moment. However, it turns out that there are ways to prevent our atomic battery from transitioning from its charged state to its discharged state. This can be illustrated using another atom, the helium atom. It has 2 protons in the nucleus and, accordingly, 2 electrons, which in the ground state are located on the inner 1s orbital. The Pauli principle states that these electrons can only be there if their spins are directed in opposite directions. If an electron were spinning, this would correspond to a situation where one rotates clockwise and the other counterclockwise. We remember that electrons do not actually spin anywhere. More details on what spin is were discussed in one of our videos. Now, let us excite our helium atom by supplying it with energy and forcing one of its electrons to rise to a higher energy level. And to prevent our electron from returning back whenever it pleases, we place the atom in a powerful magnetic field. Under its influence, our electrons orient themselves in space so that their magnetic moments, and therefore their spins, align along the field, meaning they become parallel. And this will lead to the fact that the electron from the upper energy level can no longer transition back. Such a transition will be forbidden by the Pauli principle, as it would result in 2 electrons with identical spins occupying the 1s orbital at the same time. Let us disable the external magnetic field, and after some time, the electron spins will reorient themselves again to be directed oppositely, making the transition possible. In other words, our quantum battery, consisting of a large number of such atoms, will begin to discharge. I have explained all this simply as an example. Personally, I have not heard of attempts to create quantum batteries of this specific type. What matters to us here is the principle itself. To create a quantum battery, we need to take a system capable of being in one energy state or another, then devise a way to prohibit transitions from a higher energy state to the ground state, and then devise a way to make these transitions possible again so that our battery can discharge by releasing the stored energy. One class of quantum batteries, whose research has advanced particularly far, and for which even the first experimental prototypes have already been created, is the so-called spin quantum batteries. In them, charging and discharging are achieved by measuring the orientation of atomic magnetic moments in a crystal lattice. In the normal state, the magnetic moments of atoms in most substances are randomly oriented. By applying an external magnetic field, we can make the atomic magnetic moments align. In the case of paramagnets, for example, they will align along the field. This will magnetize the material, but what matters more to us now is that such a state will be characterized by a higher internal energy value. That is, magnetizing paramagnets can be considered an analog of charging a battery. By turning off the external field, we allow the atomic magnetic moments to take on different values again. The material transitions to a lower energy state, so this process can be considered battery discharge. Quite simple, is it not? But that is just how it seems. More precisely, it can indeed be done exactly this simply, and one could even create a paramagnetic battery based on this principle. But in practice, it turns out to be meaningless. First, in the process of magnetizing and demagnetizing a paramagnet, very little energy can be stored. The specific energy capacity of such batteries turns out to be on the order of thousandths of a watt-hour per kilogram, which already makes the whole endeavor quite pointless. Moreover, to keep the paramagnet in a magnetized state, meaning to keep our battery charged, a constant magnetic field is required, and quite a strong one at that. Typically, strong magnetic fields are created using electromagnets, which consume electricity, and in practice, it turns out that maintaining a paramagnetic battery in a charged state would consume more energy than could be stored in it. Finally, the energy released during demagnetization is usually released in the form of atomic lattice vibrations, in simpler terms, as heat. Moreover, very insignificant heat, which turns out to be almost impossible to effectively collect and use for anything useful. Slightly more interesting are materials known as antiferromagnets. In them, magnetic moments are not arranged randomly, but in an orderly manner. If one atom has a magnetic moment directed, say, upward, then its neighbors in the crystal lattice will have a magnetic moment directed downward, and vice versa. When placed in a sufficiently strong external magnetic field, antiferromagnets can also become magnetized in the direction of that field. But doing so will be more difficult. That is, it will require greater energy, which is precisely what we need to increase the capacity of our spin battery. Moreover, it turns out that with some clever tricks, an antiferromagnetic material can be made to partially retain the parallel alignment of magnetic moments even after the external field is turned off. Later, the magnetic moments can be unlocked in one way or another. For example, by exposing the material to a constant or alternating electromagnetic field, like a laser field. Spin batteries based on antiferromagnetic materials are practically the only type of quantum batteries that have already been implemented in practice, although so far only at the level of experimental prototypes. Their parameters are not too impressive yet. Such batteries can store, at best, a few watt-hours per kilogram of mass. Additionally, the issues of efficiently extracting energy from these batteries and converting it into something useful, such as electric current, have not yet been fully resolved, although there are many interesting ideas here, such as using the so-called inverse spin Hall effect. Nevertheless, spin and quantum batteries in general are a cutting-edge technology emerging right before our eyes, and there is still plenty of work to be done to improve them. For example, spin batteries based on so-called topological conductors are actively being developed, as well as batteries utilizing the effect of nuclear magnetic resonance. And as for the truly astonishing idea of self-charging batteries using the so-called quantum Maxwell-Demon effect, I will definitely make a separate video about that. So all of this is very interesting. There are plenty of ideas here, and many of them look quite promising. But for quantum batteries to even come close in efficiency to classical ones, there is still a tremendous amount of meticulous scientific and then engineering work to be done. And if tomorrow you hear that someone is ready to bring a working quantum battery to market with some impressive characteristics, then most likely something is off. In general, scientists still have plenty of ideas on how to radically and fundamentally improve our energy storage technologies. And I believe that in both the near and more distant future, we will hear many more news updates about innovations in this field, which we will gladly cover in videos on our channel. To conclude the video, as usual, I want to say a big thank you to the sponsors of our channel here on YouTube, as well as on our pages on Patreon and Boosty. And if you like what is happening on our channel, then I ask you to support the project. All the necessary links will be in the description. And that is all from me for today. All the best to you, dear friends, and see you again soon.